Hey guys, so in today's lecture we'll see concentric or composite spring. So as the name suggests, concentric. So as we know that concentric circle or concentric word is used when two things are uh, two similar things like circle is inside one another circle. Similarly, here there will be two spring. There will be a bigger spring, and inside there will be a smaller spring. So the concentric or composite spring is used for first to obtain greater spring force within a given space to ensure the operation of a mechanism in the event of failure of one of the springs. The concentric spring have two or more spring and have the same free length and compressed equally. Such springs are used in automobile clutches, valve springs in aircraft, heavy duty diesel engines, and railroad car suspension systems. Sometimes concentric springs are used to obtain spring force which does not increase in direct relation to the deflection but but increases faster. Such springs are made such springs are made of different lengths. The shorter spring begins to act only after the longer spring is compressed to a certain amount, and these springs are used in governance of variable speed engines to take care of variable centrifugal force. So let me draw the diagram so it will be more clear. Suppose this is one spring. Let me draw a line. Suppose this is one spring. So there will be another spring inside it. So we'll draw another line. So there will be another spring inside this. So this is the concentric springs. So the adjacent coil of this concentric spring are wound in opposite direction to eliminate any tendency to bind. So if the same material is used, the concentric spring are designed for the same stress. In order to get the same stress factor K, it is desirable to have same spring index C. So let's see the formula for concentric spring. So here uh, so here D1 is the mean diameter of the outer spring, D2 is the mean diameter of the inner spring, then small d1 is the diameter of the spring wire of the outer spring, and small d2 is the diameter of spring wire of the inner spring. Similarly, W1 is the load shared by outer spring, W2 is the load shared by inner spring, delta 1 and delta 2 are the reflection of outer and inner spring, N1 and N2 are the number of active turns for outer and inner spring. Assuming both the springs are made of same material, the maximum shear stress induced in the both spring will be equal to tau 1 is equal to tau 2 is equal to 8 W d upon pi d cube 1111 is equal to 8 W upon pi d cube 2222. So when the stress vector Q1 is equal to Q2, then it will be W1 D1 upon D1 cube is equal to W2 D2 upon D2 cube. when K1 is equal to K2. So if both the springs are effective throughout their working range, then their free length and the deflection is equal. So delta 1 is equal to delta 2. So 8w d1 d cube n upon d raised to 4 is equal to 8w d cube n upon d raised to 4 g. So w1 d1 n1 d1 w2 d2 n n2 d2. So when both the springs are compressed until the adjacent coils meet, the solid length of the spring is equal, that is n1 d1 is equal to n2 d2. So this equation can be written as w1 d1. So using using this relation here, so we will have w1 d1 cube upon d1 raised to 5 is equal to w2 d2 cube upon d2 raised to 5. So if we divide this equation with this equation, so we will have d1 square upon d1 square is equal to d2 square upon d2 square, which is equal to d1 upon d2 is d2 upon d2 is equal to c, that is spring index. So let the spring should be designed in such a way that the spring index for both the spring is same. So from equation we have w1 d1 square is equal to w2 d2 square. So w1 upon w2 is equal to d1 upon d2 whole square. So we can find that the radial clearance between the two springs, so that is C. Now what is C? Radial clearance is this clearance is called C, the distance between the two spring. So radial clearance between the two spring is C is equal to d1 upon 2, that is radius, minus d2 upon 2, that is the radius. So what is d1 upon 2? So this full is d1, so upon 2 means this half, minus d2, so this is d2 half, so this full minus this, so we are left with this, but still we need to add the diameter, we need to subtract this diameters, so it is plus, sorry, it will be minus d1 upon 2 plus d2 upon 2. So this is the radial clearance between two springs. Usually the radial clearance between these two springs is taken as d1 minus d2 divided by 2. Therefore, so this clearance C will be equal to d1 minus d2 upon 2. So if we solve this equation, we will have d1 minus d2 upon 2 is equal to d1. So from the equation we will have d1 is equal to cd and d2 is equal to c into d2. So if we substitute these values here in d1 and d2, so we will have c d1 minus c d2 upon 2 is equal to d1. So c is a common, we will have c d1 minus c d2 is equal to 2d1 is equal to 2d1. So if we take d1 this side, so we will have c minus 2 d1 is equal to c d2. So we will have d1 upon d2 is equal to c upon c minus 2. So this is the relation for the concentric spring. So, so this is the concentric spring. So if we remember these equations, so it will be helpful in the examples. So now we'll see another topic, that is leaf spring. That is leaf spring. Now this is a very important topic, leaf spring, because it is very important at the exam point of view and also in the practical reality, because this spring is used in automobiles. So leaf springs, also known as flat springs, these are made up of flat plates. An advantage of leaf spring or helical spring is that the ends of the spring may be guided along a definite path, as it deflects to act as a structural member in addition to energy absorbing device. Thus the leaf spring may carry lateral loads, brake torque, driving torque in addition to shocks. So suppose consider a fixed single plate fixed on one end and loaded at the other end. So suppose, so this is a fixed plate, suppose of width B. Now this plate is suppose loaded at the one end, that is W, having thickness T. We'll call it as A and B, and length L. So we know that the maximum bending moment of at the cantilever beam, that is M, is equal to load into distance, that is WL, and the section modulus Z is equal to L by Y is equal to BT cube by 12 upon BT square by 6. So which is equal to Z is equal to 6 WL divided by BT square. So we know that the maximum deflection for the cantilever beam with concentrated load at the free end is will be given by, so we know the formula for deflection, that is delta is equal to WL cube upon 3EI for the cantilever beam. So here we will substitute the values, WL cube upon 3EI. Now I is moment of inertia, that is BT cube by 12. So which is equal to 4 WL cube upon EBT cube is equal to delta. So now we know that crushing stress sigma, the crushing stress sigma is equal to 6 WL upon BT square. So if we use this equation, so in this, so we will have delta is equal to 2 sigma L square upon 3 ET. So it may be noted that due to bending moment, top fibers will be in tension and the bottom fibers are in compression, but shear stress is zero at the extreme ends and maximum at the center. So if I draw bending stress and shear stress diagram, it is SFDBMD. So suppose this is the cross section. So the bending stress diagram will be such. So bending stress diagram will be such in this direction, and shear stress diagram will be such. So this is bending stress and this is shear stress. So the spring is not of cantilever type, but it is a simply supported beam with length 2L and load 2W as a center. Then then the maximum bending moment M will be equal to WL, Z will be equal to BT square by 6. Sigma is M by Z, so which is equal to W 6WL upon BT square. So BT square by 6, so 6 will go up. So we know that maximum deflection of simply supported beam loaded in the center is given as delta is equal to WL cube upon 48 EI. So W1 L1. So W1 is equal to 2W and L1 is 2L cube upon 48 EI. So if we cancel out 2 4 8 48, sorry, 2L cube here, 2 to the 4, 2 to the 4 to the 8, and 8 to the 16, so 16. So we will have here WL cube upon 3 EI is equal to delta. So this is for simply supported beam. So from this we we see that the spring such as automobile spring, semi-elliptical spring with length 2L and loaded the center by load 2W may be treated as double cantilever. So we can treat as a double cantilever beam. Now let's see the construction of a leaf spring. So let me draw a leaf spring so we'll have a clear idea. So let me draw first a center line. This and this is a center line, suppose. Now let me draw the eyes first. So this is eyes. So this is eyes. This is the first eyes. Then there is a second. So this is leaf. This is another leaf. This is the leaf. So this is leaf, and there will be bolts. So just let me label it. So, and there will be also clip, a clip, a clip, so it doesn't move out. So the first leaf or spring. So the first layer is called the main leaf. This is called the spring eye, and the distance between this center line and the first spring, this is called camber. Now this clips, the first two clips are called the U clips. It is called U clips. U clips. And here the load 2W load will be applied here, and the distance between uh, the two the distance between the two I is called 2L 2L1. We'll call 2L1. Here there is the W load is applied, and here the W load is applied. So this is the main construction of the leaf spring. So we'll see more about this in the next upcoming lecture.